Good afternoon, ladies and gentlemen. Thank you very much for the opportunity today to talk to you about looking for life on other very, very cold places within our solar system. Today I'm going to talk to you about three places within our solar system that are our favorite astrobiology targets, that is, the places where we think life could exist or still exist besides our planet Earth. A few words about myself. I am a microbiologist who specializes in polar microbiology. I do most of my research up in the high Arctic of Canada as well as sometimes in the Antarctica. Basically, I do research in the coldest places on this planet, and the primary question that drives my research is what are the cold temperature limits of microbial life on this planet? This has relevance for a number of things that are indicated on this slide. I'm mostly going to talk to you about the astrobiology implications of that question and how it is refers to looking for microbial life in places like Mars, Europa, and Enceladus. So why microbes? Why do we think there are microbes on these particular solar system bodies? The microbial world has been around for, we think, between 3.5 up to 3.8 billion years. In fact, this is a microfossil of a bacterium that we think is a cyanobacterium that was found in a rock that is 3.8 billion years. For the first 2 billion to 3 billion years of our planet, the only life that existed on our planet was microbial life, and it existed in an environment that did not contain any oxygen or very small concentrations of oxygen. And the microbial world has been here since that time and has established all types of amazing types of metabolisms that allow them to use all types of different carbon sources and things to eat and things to breathe, and that they can live in very extreme environments that, of course, we can't. So let's go to Mars first of all. Mars, 4 billion years ago, was much warmer and much wetter than it is today. Something happened about 3.5 billion years ago, and the planet has basically become very cold, very dry since that particular time till present-day Mars. Which, if you go to the surface of Mars, and we have several rovers and landers that have landed on the surface over the last 20 years. There's currently one there called Curiosity rover. This is a picture it took in the Gale crater. What we know about Mars today is that the very top of the surface of Mars is not habitable for microbial life. It is way too cold, way too dry, there is way too much radiation, and in the top 6 inches, as far as we know, the soil chemistry is also quite toxic to microbial life as we know it on Earth. But if you go below the surface, that very toxic surface environment, let's say a meter or two down, you may hit zones that bypass the radiation levels and where ice water is trapped and where there are thin films of water within that ice water that could support microbial life. And indeed, there are missions planned to do this, including one I'm involved with. It's called ExoMars, which will launch in 2020, not 2018, sorry about the slide. It has a drill on it that will allow it to penetrate the subsurface up to 1 to 2 meters, collect samples, and then bring those samples up to the surface to the instrumentation on board the rover, which can detect biosignatures, potentially biosignatures that are 3.5 billion years old. Is there a possibility that there's still liquid water on the surface of Mars today? In the last 10 years, we have discovered features, NASA orbiters have discovered features called reoccurring slope linear, or basically seasonal flows or gullies, that are flowing down the sides of craters and hills. You can see some of these features right here. They occur in the summertime and disappear in the winter. We don't really know how these features are forming, but one of the hypotheses is that cold salty water is coming from subsurface aquifers and forming these features. Are there features like this on this planet, or are there very cold salty springs on this planet, and put it another way? So I work with a place called Lost Hammer Spring on Axel Heiberg Island, which is about 900 kilometers from the North Pole. It is a sub-zero hypersaline seep in an environment that's basically about average temperature is about minus 15 degrees C. If we go into that little volcano structure that you see there, this is what it looks like. And inside this volcano structure, there is sediments and a spring at the bottom of that volcano structure, which is very interesting because there is water that exists in this spring that's minus 5 degrees C and about 25% salt. And our research has shown that there is an active microbial ecosystem that exists in that very extreme cold, salty environment. And these microbes, some of them anyways, are eating methane and breathing sulfate instead of oxygen. So this is the type of microbial ecosystem that, if you can think of this as an analog to potential life on those reoccurring slope lineae that I just showed you. Okay, we're going to go farther out into the solar system to a place called Europa. Europa is an ice-covered moon in the Jovian system of Jupiter, and underneath that ice shell that you see is a ocean that covers the entire subsurface of the planet. We think the ocean is about 200 to 300 kilometers thick, and overlaying that ocean, as you see in this slide here, is a shell of ice that we think is about 20 to 30 kilometers or 20 to 50 kilometers in depth. But there are fractures and fissures within that ice shell, and we think that there is places where water is coming to the surface. Geysers that you see here, there's some evidence of that, or the cracks that you see here and these darkening stripes that you see within Europa, which make them very interesting places that we could potentially access to collect samples in future missions to places like this. Finally, I'm going to take you to a place called Enceladus. Enceladus is part of the Saturn system. It's a very small moon, but it's one of the brightest spots within our solar system. Enceladus is very interesting because, yes, it's basically just a very small ice ball. And what makes it very special are the features that you see here, where we have geysers or jets of water that are shooting out into space. And we have the European Space Agency has flown a spacecraft through these plumes that you see here, analyzed the chemistry of what are making those plumes, and essentially what it is very cold, salty water. And that cold, salty water contains a number of chemical ingredients that you see in this part of the slide, which includes organics, nitrogen compounds, and other things. I have organisms from the Arctic or the Antarctic that could potentially, could live in this type of cocktail of chemistry that you see here. So what I'm really saying is that in the subsurface of Europa, again, there is a subsurface ocean, a cold, salty ocean that could possess active microbial ecosystems today. Finally, I'm going to show you one of our favorite microorganisms called Planococcus halocryophilus. Halo means salt-loving, cryo means cold-loving, and this is the cold temper champion of the microbial world that we know of that exists on Earth today. It was discovered in permafrost from Ellesmere Island in the Canadian High Arctic. It can reproduce at minus 15 degrees C. It can breathe and be metabolically active down to at least minus 25 degrees C. And it does this growing at 18% salt at those particular temperatures. So this is an amazing organism. This is the type of organism that could exist, or versions of it could exist on the types of habitats that I've shown you on Mars, Europa, and Enceladus today. So I'll just end this up that this is a very exciting time. In the next 10, 15, 20 years, we are sending a number of missions to Mars, Europa, and Enceladus that have the potential for the first time to determine whether or not there is life existing outside of our planet, and answering that question that is driving planetary exploration: are we alone or not? Thank you.